All right. Hi, everyone. We'll be continuing our walkthrough of the 2025 AMC 8 today. Sid will be joining in a few minutes. So I'll be starting off with problem 8. And so if you have any questions, just feel free to drop them in the chat. I'll be checking periodically as I do the problems and as well as after when I hand it off to Sid. So let's just get started. Again, I'll be doing all the even number problems, and Sid will be doing all the odd number problems, so that we both get an even share of problems to discuss. And so let's get started. Problem 8 reads. Oh, by the way, I'll be doing problem 8 and problem 10 because I think I was in a rush to actually try to finish problem 10 last time. So I'll just be starting a problem 8 and working my way forwards. So again, feel free to drop it any questions or just leave any comments or approaches that you have on the problem. And so problem 8 reads, Isaiah cuts open a cardboard cube along some of its edges to form the flat shape shown on the right, which has an area of 18 square centimeters. What is the volume of the cube in cubic centimeters? Okay, so the diagram on the right shows us like a cube and the faces that result when you cut open the cube. And so what you get is something two L shapes kind of stuck together. And so the problem tells us that this shape right over here has an area of 18 square centimeters. So see if I can make this pen bigger. Okay. Let me just actually zoom out and make these images smaller, because I think that might solve the pen issue that we were having last time. So I'm just going to do that real quick, like that. All right. And so zooming in, hopefully this works. Let's see. Okay, yeah, that's a lot better. So we're given that the area of this figure right here is 18 square centimeters. We want to find the volume of the cube. And so how should we first start about this problem? So it gives us how can we use the given information, which is that the area of the figure shown on the right is 18 square centimeters. How can we use that to solve our problem? Does anyone have any ideas? So I think the first idea that comes into mind for me is that all of the faces are squares. And so, okay, yeah, it's good that you got an answer, and I guess I'll walk through it. I guess we'll check. And so the first thing that comes to mind is that because what is a cube? First of all, a cube is basically a rectangular prism with all of its edges the same. So basically, it means that in this diagram right over here, every edge will have the same length, and so that also means that every face is a square. And so, using that information, we can see that the net is basically another way of saying, like, after you cut open the box and then just basically flatten it out, the net will consist of 6 congruent squares. And so if we label the side length of the squares s as a variable s, then we can say that because each of these 6 squares has an area of s squared, because remember that for a square of side length s like that, the area is s squared. Then it's easy to see that the total area here is just 6s squared. All right, does that make sense to everyone? The total area is the total area of the net is 6s squared. And so because the problem already gives us that the net has an area of 18, we can say that 6s squared is equal to 18. And remember that we don't necessarily need to solve for s in this problem, because it asks, again, it's a really important strategy to like focus on what do you need to solve in this problem. What is this problem asking you? And so because the problem asks you for the volume of the cube, we actually want to solve for s cubed at the end of the day. And so with this idea in mind, we don't actually need to solve for s, and we can let's see how. Actually, of course you can solve for s, and then cube that, but that's just this is use some algebra to actually get s cubed by itself. And so because 6s squared equals 18, we can divide by 6 on both sides. That gives us s squared equals 3. And look what we can do here to get s cubed. We can raise both sides to the 3/2 power. And by exponent rules, we know that if we have some quantity a to the b and raise that to the c, that's going to give us a to the b times c. And so applying that property, we can see that the left-hand side in our original equation involving s gives s cubed, because 2 times 3/2 is just 3. S cubed equals 3 to the 3/2. And so obviously we don't see 3 to the 3/2 in one of the answer choices, but we can actually say that 3 to the 3/2 is equivalent to 3 to the 1 plus 1/2. And again, if you recall more exponent rules, a to the b plus c is equal to a to the b times a to the c. And so that kind of like makes sense, because if you have b copies of a and c copies of a, you're gonna get like b copies. You can just multiply b copies of a and c copies of a together. And so you can still do that with fractional exponents. It still works the same. So that's just 3 times 3 to the 1/2. And 3 to the 1/2 is just root 3. And so that's just 3 root 3. And I believe that someone in the chat said, or let me see, 3 to the, 3 to the, correct me if I'm wrong, by the way. I'm just checking because someone in the chat, I got something different. And so s cubed is 3 square root 3, and so what I got is a. So again, as I'm solving this in live stream, I'm not gonna always be correct. And so sometimes one of the problem solving strategies that I want to introduce to you guys is kind of like rereading the problem statement to check if you're actually missing something. Because usually I like to read problems twice just to like enhance my accuracy. Ooh, where did my problem go? Okay, there we go. Okay, so rereading, it says opens a cardboard cube. I don't think we're missing anything with that along any of the edges of flat shape shown on the right. So sometimes they have something really tricky. Sometimes they say like, oh, it's half of the area is like 18 or something like that. So that's why sometimes it's a good idea to always read the problem twice. So the area of 18. What is the volume of the cube? And so we had the setup 6s squared, because there had to be there are obviously six faces in the cube, and so so because each face has area of s squared, if s is the length of the cube, then there are the area is 6s squared. We divided by 3, and we took everything to the 3/2. And so yeah, it should be also root 27 if you think about this as like 3 cubed to the half. And so it should be root 27, which is 3 root 3. Yeah. Anyways, I'll just check. And of course, like I would the thing I want to encourage you guys is that like making mistakes is actually one of the best one of the best lessons that you can that you can learn from like math competitions, because like um, I think okay, as I'm searching the answer up, I think it's in general it's like it gets it I guess it's kind of like sucks to make a mistake like after a contest, um, knowing that you could have gotten the problem correct, but it's also like a really good learning experience because now you know what not to do and what you can do to prevent that from happening in the future. And so then just check, yeah, 3 root 3 is the right answer. And so um, feel free to also like drop like what you did wrong, because like it can also help others to like learn from your mistake, and like also improve themselves too. So it all again it's a math this like math competitions for me it was a really long journey, and um mistakes are really like one of the best stepping stones that you can that can help you improve. And so A is correct. Let's just move on um to the next problem. And so problem 10, I'm going to redo it and probably just redraw the diagram because I don't think you guys can see that. So let's just do that real quick. Okay. All right, problem 10. In the figure, yeah, again, I'm going to draw the diagram. It's sometimes it's a good thing to redraw the diagram on the scratch paper, especially in harder contests. But again, like the AMC won't always give you a diagram to draw, or they won't always give you a diagram. And so it's a good practice to actually like know how to draw what's going on, especially in geometry, because uh, if you're doing harder concepts like the AMC 10 or even like the SAT, they might not always give you like a diagram to rely on. So you drawing skills is a really important skill to know how to do. So um, anyways, it states that ABCD is a rectangle with side length AB equals 5 and AD equals 3. So right off the first sentence, I always like to draw, like just start drawing something. Even if it's wrong, you can redraw it later after you finish reading the problem. But you just want a good sense of about like what does it look like approximately. It doesn't have to be perfect, but you just need to know what's going on. And so AB is 5 and AD is 3. All right. And so it also gives us that ABCD is a rectangle. So we know that AB is equal to CD. So I'm just going to write a 5 next to CD right there. And AD equals BC. And so I'm just going to write a 3 right there. And so rectangle ABCD is rotated 90 degrees clockwise around the midpoint of DC to give a second rectangle. And so what's the area in total square inches covered by the two overlapping rectangles? Okay, so let's actually draw what ABCD looks like in when it's rotated 90 degrees clockwise. And so it states that it's rotated 90 degrees clockwise around the midpoint of DC. And so we mark midpoints of segments if you have another segment EF and you want to find the midpoint, you should mark a point that's around like halfway, because that's like a definition of a midpoint if you call it M. But you should definitely mark like these tick lengths right there, just to mark equal segments. And so that's what I'm doing right here. This point right over here is a midpoint of CD. And so when you rotate it, if you imagine just like if you don't know what it looks like at first, you can first draw it like that. And so it should be rotating it about this midpoint 90 degrees. should give you, well, it's really helpful to envision where the points are. And so A should be around, let's see, A should be around like here. B should be around here. And oh, sorry, this is D. This is D. C should be around here, and B should be around here. So it should be like that. Again, this comes from a little bit of practice, because transformations, that's what transformation problems are all about. It's kind of like visualizing where the new points uh, go, and how like the new how the new image corresponds with the original image. um, and so we can try to draw it right now, actually. So with this like idea, we can just kind of like copy what we did, except we need to be a little bit careful, because let's just try to draw DC first. D prime, if ABCD maps to A prime, B prime, C prime, D prime, then D prime is gonna stick out like that. It's gonna this like this green segment is corresponding to this green segment, like that. It's just gonna like be rotating 90 degrees. That's what the problem tells us. So erase this phi real quick. You know that is phi. So this is gonna be C prime. And so this segment CD is gonna be like that. It's gonna stick out like vertically. And so we just mark the equals lengths like that. And so we got to be a little bit careful when we draw a segment like AD in our image, because we know that what's the length of this tick mark? It's going to be 2.5, because the midpoint is exactly halfway between C and D, and we know that CD is 5, so D to the midpoint has to be 2.5. And so the same thing for all these tick marks. So that's 2.5. And so when we draw A, do we draw it inside or outside? So does A go here, or does A go here? What do you guys think? Because we're rotating it by 90 degrees clockwise. Does A go inside the rectangle or outside the rectangle? What do you guys think? Any ideas? If not, that's fine. It has to go outside. And the reason being is that we know that AD is 3. So A prime, D prime has to be 3, because like a rotation about something, it doesn't really change the lengths of the rectangle, right? So A prime, D prime has to be 3. And so because A prime, D prime is 3, and C prime to the midpoint, let's call it M, CM is 2.5, and we know that A prime, D prime is parallel to CD, and that's because we just rotated by 90 degrees. We know that A prime has to be outside of ABCD, and so it's gonna look something like that. And so the reason why it can't be inside is that if it was inside, then I'm just gonna mark it like, if A prime was like here, and you're just basically saying that this pink segment is 3, and okay, get rid of these green segments. This green segment CM is just 2.5. So you're saying that 3 is less than 2.5, which is not true. And so it has to be outside. And that's a little bit of a visualization trick. It's a little bit tricky to visualize, but once you realize that like CD is parallel to like the new image of AD, then you know that it has to be outside. And so the problem's basically finished. The main idea was kind of like trying to visualize how to rotate the rectangle. And I know this wasn't like any like sort of like rigorous proof that A prime was like outside, but let me know if you guys want like a further explanation of why a prime, b prime, c prime, d prime should look like this. And so we know that now we just need to let me see. I'm just making sure if I'm doing it right. Covered by the two. Oh, okay, yeah. So okay, we know what it looks like now. Um, Now what do we do? What is it asking us? We want the area of the two overlapping. What's the total area covered by the two overlapping triangles? And so the total area is gonna look something like this, right? Whatever is covered by at least one of the two rectangles. And so, how do we calculate the area? Well, you may be tempted to say, well, there are two rectangles, so I'm just going to add up the areas of the two rectangles. Well, that's not how it works, because if you have an overlap, we got to subtract the overlap. Because if you imagine, let's say you wanted to, let's see what's wrong about adding the two rectangles together, the areas of the two rectangles together. Let's mark the area covered by the first, like the original rectangle, pink, and the area of the second rectangle, the image, blue. Okay, so we're just going to color it in. So let's say you add the area of the first rectangle, like that. All right, it's going to, everything covered by the pink is ABCD. And so, okay, so you added the area of ABCD. Now you're going to add the area of the image. And what's that going to look like? That's going to look like this. And by this point, you can see why you can't just add the areas of the two rectangles. So obviously, like there's an answer choice for this, but if you were to add up the areas, it's going to be like 15 plus 15, which is 30, and that's not an answer choice, thankfully. So we need what's wrong about that? Well, there's some overlap here, right? Because the overlap is it's counted twice, and so we needed the area of the overlap. We need to subtract the area of the overlap from our sum. And so we can say that the total area, so the area covered by rectangles. And so that's just ABCD. Again, I'm using the bracket notation to denote area. So the bracket just means the area of something. So the area of ABCD times the area of A prime, B prime, C prime, D prime minus overlap, the area of the overlap. So what's the area of the overlap? Well, let's just get rid of the colorings for a sec. The overlap is a rectangle, actually, because you rotated everything by 90 degrees. The intersections will be 90 degrees, just intuitively, So, and let's just see what the sidelines of this overlapping rectangle, I guess shown right here. The length is 2.5, just this much, and the height, or well, sometimes I confuse like height, width and stuff. This should be just 2.5, right? So this times this is actually just a square like that. And so the overlap should be, well, let's just compute the areas first. The area of ABCD is 3 times 5. The area of its image is the same because you're not changing anything by rotation by a point. 3 times 5 times 3 times 5 minus the overlap, which is 2.5 times 2.5. And so that's 2.5 squared. And so we can just do the computation. That's 30 minus 6.25. Uh-oh. Uh-oh, wait. Yeah. Okay. And so that should be 23.75, if I'm not wrong. Yeah, 23.75 is an answer choice, and we just check. Sometimes I like to check with computations. There's 15 and 15 for the rectangles, and that's subtract 6.25, 30 minus 6.25. And yeah, that should be 23.75. If you add, obviously you can just check it real quick. like that. Again, it's a 0, 1, 0. Yeah, and that gives us 30. Yeah, so it should be 23.75, which is D. And that's our answer. Let's just check it real quick. This is problem 10, I think. Yes, that is correct. All right. Okay, I want to walk through. I think I started a little bit late. I want to walk through problem 12 real quick. So if you guys have any questions about the two problems I already covered so far, feel free to ask them, and I'll be happy to answer them. So I'm gonna walk through problem 12 real quick, which I think I did look at. This was one of the only ones I looked at beforehand. I thought it was kind of cool, but you also have to be careful, and so you'll see why in a sec. The region shown below consists of 24 squares, each with side length 1 centimeter. What is the area in square centimeters of the large circle that can fit inside the region, possibly touching the boundaries? Okay. I think this is a really good exercise to kind of like be careful, because often what they like to do is to um, make you find a possibility that is not the largest or the smallest. Because when it says largest, you have to be absolutely sure that like it's the largest, it's the smallest, it's the largest in this case, is the largest possibility of a circle fitting in this region. And so, how do we get started here? As I have to hand it over to Sid in a very soon, I'm gonna the thing I like to think about of circles and grids is that like if you have something that's like that this problem reminds me is like if you have or okay, I'm gonna make a new grid right here. Actually, I think there's a better grid would be like this. So something that I'm thinking of is like if you have a grid like that, a 4x4 grid, and you want to inscribe a circle in it, the largest possible radius is 2. Because if it's anything greater than 2, the circle is going to like emanate out like that, and it's going to hit each of the sides twice and go outside. And so we don't want that. The radius of this is just 2, right? And so thinking about this idea, and again, like this is not really like arbitrary. Like something that comes with a lot of problem solving is like you get to see the connections between one problem and like a distinct problem. And so this is like a sub problem that I'm immediately thinking about when I see like a grid and like the largest circle. And so we can, using this idea, we can actually just say, well, could it be this, right? And again, the area, what's the area? It asks for the area, not the radius, but it doesn't really matter, right? We just want to, finding the largest radius of the circle is equivalent to finding like the largest area. And so the area is just pi squared, right? And so with this possibility, we can say that, okay, well, r is 2, and so the 4 pi works. And so the answer is not A, can be B, okay? That's nice. But can there be another one? And this is where like for these problems, you gotta like draw out. You have to be absolutely sure, because if you found one possibility, there could be another. So let's just try for another one. Let's just try to shoot for 5 pi, right? Well, if you have 2 grid lines and 1 grid line, right, like that, you're gonna have a radius of root 5, because like this triangle that I just drew right there has legs of 1 and 2, and by the Pythagorean theorem, the hypotenuse is root 5. And so if we have the hypotenuse is root 5, we can draw a circle that looks like this. Draw my best to draw it. Like that. And it goes out like that. Okay, well, that also works, because even though it isn't tangent to like the 4 sides of the center rectangle, it works, because all it has to do is to, fit inside the region, but it can also or touch the boundary. So it touches the boundary, it also fits inside the region. So with that, r equals root 5 works. R equals root 5, and thus the area of 5 pi works. So B can be right. Okay, this is what I mean by like trying. You have to like guess and check. You have to guess and check like this is the maximal. So let's try to aim for 6. Um, it is a little bit tedious for problem 12 in my opinion, but this is what we gotta do. Okay, let's see. 6, how can we get 6? We can get 6 by getting this, right? Or no, my bad. 6, I'm thinking of, again, I'm thinking of two integers such that the sum of the squares is 6, so that we can apply the Pythagorean theorem. And so what can we do here? We can get, can we actually get 6 from a sum of two squares? So 1 squared, we can't have 0 because that doesn't make sense. It's a straight line. So 1 squared plus root 5 squared. Well, again, like we want tick marks because I don't think that works. Also, let's just like draw our original circle like that. Oh, that, 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 that. Intuitively, though, right? If we think about like this point, like that, intuitively, we should be able to deduce, even though we want to like try to get 6, right? If we like enlarge the circle a little bit more, right? If we zoom in all the way, and this is something that you want to like do in the contest, and not like of course you're not gonna have like this like ability to like actually zoom in, but if you have just a little bit more of radius, and you're just gonna hit outside the circle. So we should have an intuitive sense that 5 pi like C 5 pi is our answer. We can just check like 6 doesn't actually like shouldn't have any like lattice point, or it just shouldn't be any radius with 6. And so 1 squared you're gonna have to have root 5. That doesn't work. 2 squared plus 2 squared plus root 2 squared, that's not going to work. Root 3 squared, then that's too big. And so we're not going to have a lattice point on this grid such that the distance from the center to that lattice point is going to be root 6. We're not going to have that. And so that does bring up some issues because that we can't be really sure that like because the circle doesn't hit the any lattice point, we're gonna have to like use our intuition to actually reason that 5 like root 5 is the maximum radius. But that's but again, like as I mentioned earlier, if you have a little bit of outside radius, just think about what happens if you go like outside here. You're gonna hit some points in this yellow region right here, and so that's not good because we want our circle to be completely inside this grid. And so I believe the answer should be 5 pi. Because if you have any more radius, any more length, it's just going to hit outside of the circle. And yeah. So 8 pi is really easy to check because 8 pi can be achieved like that. However, if like this red length is the radius, which has radius root 2 to root 2, you're gonna have something like that, which is no good. Because you get some area over here outside of the grid. So 8 definitely doesn't work. Looking at this first time, I'm actually not sure if 6. I don't think 6 will work. So the answer should be 5. Again, this is my intuition for like 6 not working is like if you have any extra radius, and then the circle is gonna get outside of the grid, and we don't want that. So let's just check 5 pi. I mean, 12. Yeah, it's problem 12. Yeah, and it's 5 pi. All right, and so that was problems 8, 10, and 12. If you have any questions for that, leave in the chat, and of course I'll be around to answer it. And so Thank you, everyone, and I'll hand it over to Sid now to cover some of our odd number problems. Thank you, guys.
Hi. So I'll be covering the odd number problems as Daniel mentioned. You guys can hear me fine, right? All right. Uh, I'll just share my screen real quick. Can you guys see the problem? All right. So the problem says a tetromino consists of four squares connected along their edges, right? There are five possible tetromino shapes, which is just so I, O, L, T, and S, right? And these can be either be rotated or flipped over. So you could have, so let's say we're looking at I, right? So you could have I like this, or you could have I like that. So it's like it can be rotated or flipped over, right? So three tetrominoes are used to completely cover a 3 times 4 rectangle. So we see here a 3 times 4 rectangle. And it says that three of these shapes, so like either two of I and one of O, or two of L and one of T, something like that, right? So it says that three of those tetrominoes can be used to cover a 3 times 4 rectangle completely. And so, one condition says that at least one of the tiles is an S tile. So what are the other two tiles? All right. So I'm just gonna erase this real quick just to make space. Actually, I'll just redraw the 3 times 4 rectangle. So we have something like this. So that's one, two, three. Forgive me for the uneven spacing, but yeah. So S is this is S. So we have to. So let's draw the shape here. So something like that, right? So this can be flipped over as well, right? Um, so first we go through some configurations and see what won't work. So like in terms of placing S and what could work, right? So let's say you had S like this, right? So um, I'll just draw it in a different color. So say this was S, right? So say this is the configuration that we choose for S. So we place the tiles here, and then this is the configuration that we choose. Well, this won't work, right? Why? Because look at this square. We might be able to fill these squares, right? But how about the square? How about the square in the right, right, or square in the top left? We're not going to be able to fill those squares in, right? Fill that square in because uh, I'll just draw this in red. Yeah. All right. So we're not going to be able to fill this square in because because in none of our given tetromino configurations is there just one square that we can use to fill this square, right? So obviously this is not a very valid configuration. So let's so let's redraw the whole thing. So one, two, yeah, right. So obviously that didn't work. Well, but we have to place the S somewhere. So do you guys have any ideas on what could work? If I placed it here, if I say I placed S here, um, say I placed S here, right? Something like that. Say this was the configuration that we chose for S. Would that work? Well, at first glance, you might not say that won't. You might say that won't work because we have two squares here that we want to fill, right? And two squares we obviously don't have any configurations here that could solve the problem. But what if I tell you that we can actually make this configuration work? We can make it work. Okay. We can make it work because you see that the shapes filled over, or the shapes left over, can actually be filled in a continuous way. So um let's so you see this. You focus on this side right here. You see, you see these are four shapes that are filled together. But now let's look at if these four shapes are actually in our given list, right? No, that's not it because that's just four squares in a row. That's not it as well because it's not a grid of two times two squares. Is that it? No, that's not it as well because we need almost like an L-shaped thing. Uh, Obviously we can't have that, right? That's not it as well because it's not L-shaped. Look at L. Is L can L is L the right option? Yeah, because it says that it can be rotated or flipped over. So uh, if you rotate L about its axis, or like I guess if you rotate L 180 degrees, that's what you get, right? Like you get this option. You If you rotate L 180 degrees, these vertical three squares stay the same, but the horizontal square changes direction, and that's exactly what the square is, right? So this is an L. This is our S. Well, now let's look at the squares that are left over. The squares that are left over now, because these squares are already covered by the S, right? These squares are already covered by the S, right? That's the S shaped, and that's the S shape. But now we look at the squares that are left over. These are the squares that are left over. Well, what's this shape? It's an L again, right? Because this was an L. This was an inverted L. Now you rotate L by 90 degrees, right? If you rotate L by 90 degrees, you should get something like this. See, that's what you get when you rotate L by 90 degrees, and that's exactly the shape that we have here. So what were the two other shapes that we needed? So what are the two other tiles? Well, we needed an L here and we needed an L here. So the answer is C, L and L. So we need two more L's to complete the shape. Also, what you gotta realize is that there's only a couple of ways to even place S in this figure here. So you could place it like that, right? So that's one way. Um, you could place S like S. You could like shift S up here as well, right? That's another way, right? But like there's only a couple ways that you can even do this. So you can have something like that as well. And you see, okay, this was one different. This is a good way to check our work actually, because if we find two different configurations and they give us the same two other tiles that need to be filled in, we are confident that this is the right answer, right? Because the AMCA only wants us to choose one answer, and if we get two different configurations and they both lead us to one answer, and we know that this is the right answer, right? Because they know that at least one of the tiles is an S tile, and so what are the other two tiles, right? So we have an S tile right here, and it's completely different from what we had here, right? This was in the bottom left, this is in the top right. Well, look again, right? This is an L-shaped tile again, and this so you see so okay. Does this shape work? First of all, no, right? Because obviously there's only three tiles here that we have to fill, and uh, actually, yeah, this does work, right? Because that's my bad, guys. Sorry. This does work because uh, I'll show you guys just in a second. Um, so you see, this configuration is one L, or wait, yeah. So my bad. I just drew the shape of square too long. This is the configuration for L. You have four squares. It's a tetragonal, right? And then this is the other configuration for the other L, right? So you see again two L's, L, L, and an S, right? So you know that L and L must be the right option. Does that make sense, guys? Does that make sense to you guys? By the way, let's try placing, uh, just erase this. Let's try placing, oh, yeah. So let's try placing two S's, right? Because we experimented only with one S tile, and we both and both times we got an option of L and L. Well, let's try two S tiles, right? So we but you see, you see, two S tiles wouldn't actually work. And this is because you need to read the problem statement. The problem statement clearly says things like logically means that there must only be one S tile. You can't have two S tiles because, and this is a very good strategy that you guys should use in competitions as well as if even if you take the SAT and so on, right? Because reading the problem statement often gives us a lot of information about what we need, right? And not reading it can lead you to wasting time, right? Due to infutile attempts of getting something that really doesn't even exist, right? It said the problem statement says that three tetrominoes are used to completely cover a 3 times 4 rectangle. So that means that there should be three tetrominoes in total that needs to cover a 3 times 4 rectangle. You can't have more than three tetrominoes. So you can't have five tetrominoes. You can't have four tetrominoes. It has to be exactly three, right? And so it says that one of the tiles is an S tile. Okay, if you have two S tiles, if you have two S tiles, then what must the other tile be? Something else, right? So we must have one other tile. We must have one other tile. Well, what does the problem statement says? The problem statement says what are the other two tiles? So they want two more tiles. But if we have two S tiles, we can only get one more tile, right? So that means that the number of S tiles in this problem has to be one. Can't be two because then there's only one other tile, and the problem statement says that we want two other. Right. So does that make sense to everybody how we approached this problem and how we got like multiple configurations that led to the right answer? And so that's a very good way of checking your answer, I believe, in the competition as well, because it really doesn't take that much time to like draw the configurations and like or draw at least two configurations at work and just see if you're right or wrong, because two is basically like guaranteeing your uh answer choice. Right, so does that make sense to everybody? I'll just pop questions in the chat, by the way, and Daniel will be sure to address them. All right, so moving on. So problem 13. What does problem 13 say? Problem 13 says each of the even numbers 2 to 50 from 2 to 50 is divided by 7. And so the remainders are recorded. And so which histogram displays the number of times each remainder occurs? So let's try to understand what the problem is saying. The problem is saying, okay, I have uh, all the even integers, all the even numbers from 2 to 50. We have all the even numbers from 2 to 50, and we're dividing them by 7. And we record the remainder. So what we are basically getting is we're getting so let's say an even number from 2 to 50 is x, right? We are getting x mod 7. So that's what we are getting. We are getting x mod 7, and the histogram. So this is these are the remainders that are arranged in the histogram, and says which histogram is the number of time each remainder occurs. So basically, we should learn how to read a histogram first of all, right? So the histogram in the okay. So the histogram, what it does is that it's going to give you the remainders in the bottom. So 1 0 1 2 3 4 4 5 6. Obviously you can't go more than 6, right? Because 7 mod 7 is 0, so it just repeats again. So it's just going to repeat from 0 to 6 and then 0 to 6 and then 0 to 6 again and again, right? So but what we want here is we want to find okay, and so these are the remainders, and then it says the count. So what that means is that okay, 0 appears 3 times, from if we take the remainder of x mod 7, so like all the even integers, we take mod 7, 0 appears 3 times, 1 appears 4 times, 2 appears 4 times, and so on. So that's how you read the histogram. It's the number on the top is going to give you the number of times that the remainder appears inside the set 2 to 50, inside the even numbers in the set 2 to 50, right? So what you want to do in this problem is, why don't we try to use elimination, right? So we're given 5 answer choices and we want to bring it down to one. Well, let's try doing that, right? So first we see that we can easily find the 0 mod 7, because what does 0 mod 7 mean? 0 mod 7 means that the even integer is divisible by 7. If the even integer is divisible by 7, that means that the number is 0 mod 7. So how many integers even are there that's divisible by 7 and is between 2 and 50? Well, let's see. So we start from 14, because 7 times 2 is 14, right? That's the lowest even integer, because the lowest multiple of 7 that's even in the set is 7. And so the lowest even multiple that's in the set of 2 to 50 that's a multiple of 7 is 14. How about the highest one? Okay, so we go from 14. We keep adding 14s, because that's how we're gonna get the multiples of 7. We keep adding 14s, because remember, we don't have all we could have added sevens, but we don't have odd numbers in the set. It's only even numbers. So we add 14 more, we get 28. We add 14 more, and we get 42. We add 14 more and get 56. Oh wait, 56 is not even in the set, because it says 2 to 50. So you cross out 50, and we see that there's only 3 even integers that are multiples of 7 inside this set. So we can definitely cross out D and E, because they have 4. So now our answer choices are between A, B, and C. Right. Does anyone have any questions on how we approach that? Well, now let's look at hmm yeah. So let's look at So now let's be a bit strategic about this. So we have one, the remainder one appearing 4 times here. So we have 4 here. So that's not going to help us, right? Because all the answer choices are the same thing. We're wasting our time if we do this, because we're going on an elimination approach. How about remainder two? Well, we see the remainder two is also 4 times, right? It's 4, 4, and 4. That's not going to help us eliminate any choices. Well, how about we look at remainder 3? Well, remainder 3, we see that here it only appears 3 times, but here and here it appears 4 times, right? So that's gonna help. Like, so you see how that's gonna help us eliminate a choice, because if we find that the remainder 3 appears 3 times, well, we know that the answer choice is A. But if we see that it only appears that it appears 4 times, at least we have A crossed out, right? So that's different, uh, right? And so let's try to find all the remainder threes that are even multiples of 7, or uh, all the even integers inside the set 2 to 50 that are multiples that are has a remainder of 3 when divided by 7. So first, what number do we start with? Well, we want to find a number x mod 7, which is equal to 3, or uh, you don't have to do that. You just say equal to, right? Well, look here. Well, we look here. We see that x mod 7 is 3, right? Well, we notice that 7 is an odd number and 3 is an odd number. So we know that all these numbers are in the form 7, a plus 3, where a is a positive integer, right? That's all the numbers of this form, right? We see that if a equals 1, because it has to be a positive integer, if a was 0, then x would be 3. 3 is not an even integer, or even number between 2 and 50. Well, if a is 1, if a equals 1, x is equal to 10. Is that viable? Yeah, that's viable, right? That makes sense, because you obviously have uh, 10 is an even number. It has a remainder of 3 when divided by 7. That works, right? And it's between 2 and 50. Well, now we remember that since we are counting by since we're counting up by uh, we're since we're only looking at even multiples, the next mod 3, the next mod 7 being 3 will appear at 24, because you add 14s just like you did here. You add 14s here to get to the next mod zeros, to the next 0 mod 7s. You add 14 here to get to the next mod 3s, mod 3 mod 7s, right? So you have 10, you have 24. If you added 7, you would have gotten the 17. Well, 17 mod 7 is 3. Well, what's the problem here? 7 is not even. You have to add 14, because that's how you get to the even integer, skipping over the odd. So you add 24, and then you have 38, right? 10, 24, 38. That adding 14, and then you have 38 plus 14, which is 52. Oh wait, 52 doesn't work, right? Because 52 is greater than 50. You only want numbers from 2 to 50 that are even. That doesn't work. So you find that there is only uh three numbers that give a remainder of 3 when divided by 7. So we look at answer choices here. B is not right because it has four integers that give a remainder, uh, four integers that give a remainder of 3. This also has 4. So our answer here is A. Does that make sense to everybody? How I went on a more elimination type approach. I feel like this would probably be the most important or most useful approach in this problem, because it really gives you a quick way of doing it. Obviously, I'm walking you through this problem, which is why it's been taking me a bit slower. But this is really a quicker way to do this, and it's really an approach that will save you a lot of time in various different multiple choice contests. So definitely keep this approach under your belt, and also be clever using it, because you don't want to use that on, say, remainder 1, because remainder 1 has 4 and 4 on A, B, and C. So that's not going to help us. That's not eliminating anything. The same with remainder 2. Remainder 3, however, it gives you three numbers in A, but four numbers in both B and C. So obviously, if you use that, that could lead to something, and in this situation, it did. So just keep this approach in mind when you solve these types of problems. And so our last problem that we're going to cover in this session is this one. So K draws a 6 by 6 grid. He colors 13 of the unit squares silver, the remaining squares gold. K then folds the grid in half vertically, so like something like that, right? So he folds the grid half vertically, forming pairs of overlapping unit squares. Let M and M be, so M is least and M is greatest. What is the value of M and M? Well, if you're coloring 13 of the unit square silver, what should you do to reduce the number of gold and silver pairs, or gold on gold pairs? What do you want to do? Because you have to reduce the number of gold and gold pairs, right? So what you want to do here is actually the optimal approach would be doing something like this. So just go with the time. Yeah, so you have 4 minutes. So if you want the least number of gold on gold pairs, what you want to do is you definitely want to have all the silvers on one side, because when you pair it with the gold on the other side, it's going to give you gold and silver, gold and silver, gold and silver. And so that's how you get the least number of gold and gold pairs. So we don't want gold and gold pairs. We want gold and silver. So what we do is, since we're only allowed 13 of the unit square silver, so this is 3, this is 3, this is 3, this is 3, and this is 1. So this is 1. So these are all the silver squares that I'm coloring, and everything else is gold. So what that means is, when he folds the grid in half, or yeah, so when he folds the grid in half, these squares, all of these will be basically all of the other squares except these 13, all the other squares will be gold, right? So that means that if you fold it apart, all of these pairs will be gold and silver pairs. The only pairs that'll be gold is these pairs, and you see we have 5 of these. So the lowest number is 5. So we want the highest number of gold pairs by doing exactly the opposite of what we did here, right? So we chose all the different gold and silver options to be on one side, but on the on gold to want the highest number of gold and gold pairs, we want we want the um, right. So we want the number of gold and gold pairs to be highest. And so what we want there is we want the silver to be across each other. We want silver something like this. So these are six pairs of silver. Because if you have silver six pairs of silver, then the other will all be gold, right? And so you have so many gold and gold pairs, right? And that's going to be the maximum. You can try other cases in your own time, and that'll yield you different results, right? So these are six silver pairs. These are six, and then this is one, right? So we see that there is going to be um, you see that this is all going to be gold on gold pairs, right? So this and this, right? So we see that there's 9 plus 2. So 9 plus 2, 11 gold on gold pairs. That's the maximum that we found using this configuration. And so our answer is going to be m plus m is 16. And you can try other cases to find optimality, but this is definitely the most optimal case for finding gold on gold pairs.